Hello students, I hope you all are doing good. The topic that we are going to discuss today is current electricity, example 3.1 and 3.2 and NCERT section 3.5.1 to 3.7. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So here is the index, the topics that we are going to cover today. First one is example 3.1, example 3.2, NCERT section 3.1.1 mobility, NCERT section 3.6 limitations of Ohm's law, and NCERT section 3.7 resistivity of various materials. So our first topic and first example 3.1 and its A part. Estimate the average drift speed of the conduction electrons in a copper wire of cross-sectional area 1 into 10 to the power -7 meter square carrying a current of 1.5 ampere. Okay, so we have to estimate the average drift speed of conduction electrons in a copper wire having cross-sectional area given and also current is given. Assume that each copper atom contributes roughly one conduction electron. So in conducting copper wire, each copper atom contributes only one electron. It means in this wire, number of electrons is equal to the number of copper atoms. Okay, so number of copper atom is same as number of electrons because each copper atom is contributing roughly one conduction electron. The density of copper is given 9 into 10 to the power 3 kg per meter cube and its atomic mass is also given 63.5 atomic mass unit U. Okay, so let's see the solution. The direction of drift velocity of conduction electron is opposite to the electric field direction. So direction of drift velocity will be opposite to the electric field direction. Why? Because electron experience force in the direction opposite to the electric field. So their drift velocity will be having direction opposite to the electric field direction. That is electron drift in the direction of increasing potential. Okay, so direction of electric field is in the direction of decreasing potential and electrons are moving opposite to the direction of electric field. That's why they are moving in the direction of increasing potential. Means they are moving towards positive, but more positive potential. Okay, in the direction where potential is increasing. The drift speed Vd is given by equation 3.18. In previous lecture, in yesterday's lecture, we have derived the expression for drift velocity. That was Vd equal to minus E capital E tau upon m. Okay, again after that we derived the relation between the drift velocity and current. Okay, so this relation is marked as equation 3.18. That 3.18 equation, according to that, Vd is given by I upon NEA because I is given by NEA Vd. So Vd is given by I upon NEA. Okay. Now E is given, this I is given and this A is given. E is known. What is E charge on an electron is 1.6 into 10 to the power -19 coulomb. Area is given in the question, which is 1.0 into 10 to the power -7 meter square. Current is given 1.5 ampere. The density of electrons n. Now we have to find just this n, number density. Number of electrons present in the conducting wire per unit volume of the conducting wire. Okay, volume is not given. Volume is not given in the question. We have to find the number density, number of electrons per unit volume. So the density of conduction electrons n is equal to number of atoms per cubic meter. which is assuming one conduction electron per copper atom and is as is reasonable from its valence electron count of 1. Okay, so valence electron is 1 in this copper material. Okay, there is one electron that is free to move, so one copper atom is contributing to one electron. Therefore, number of electrons will be equal to the number of copper atom present in the conductor. A cubic meter of copper has mass 9 into 10 to the power 3 kg. Okay, since in 63.5 U is the atomic mass of the carbon. 63.5 U is the atomic mass of the copper. So 63.5 gram copper will be having 6 into 10 to the power 23 copper atoms. That is Avogadro number. Okay, so that is Avogadro number. Means atomic mass, if we are taking it in gram, and this is molar mass 63.5 gram, so it is having Avogadro number copper atoms. So how many atoms or how many particles will be having, how many copper atoms will be having in 9 into 10 to the power 3 kg of copper? Okay, so we know that this can be also written as 9.0 into 10 to the power 6 gram. Okay, we are converting it into gram because for the calculations we are taking gram here, so we have to take gram here also. Okay, so 9.0 into 10 to the power 6 gram. This in this amount of copper, how many atoms are present? Okay, so what we are going to do, so n, number density, is equal to 6.0 into 10 to the power 23 upon 63.5 into 9.0 into 10 to the power 6. How this thing came, I will explain. Okay, so it is given that in 63.5 gram of copper, because 63.5 U is the atomic mass, if we are taking it as gram and molar mass, so 63 gram of copper will be having Avogadro number atoms, means 6 into 10 to the power 23 copper atoms. Okay, so 1 gram of copper will be having how many atoms? 6.0 into 10 to the power 23 upon 63.5. Okay, so now this amount of 9 into 10 to the power 3 kg, or we can say 9.0 into 10 to the power 6 gram of copper will be having how many atoms? Upon 63.5 into 9.0 into 10 to the power 6 gram of atoms. Okay, so this amount of atoms will be there in copper atom, but volume is not given, but density is given. What was the density? 9 into 10 to the power 3 kg per meter cube. So if volume is not given, we are taking unit volume, 1 meter cube. Okay, so this is the density. This amount of mass is present in 1 meter cube. Okay, so if we apply meter cube here, per meter cube, so this amount of this mass of copper per meter cube having number density of electrons, this amount per meter cube. Okay, so this amount of copper atoms per meter cube is present. Okay, this amount of copper atom present in per meter cube, that is the number density, that is number of copper atoms per unit volume present in the 1 meter cube of copper material. Okay, so it is also given n is equal to, now after solving, 8.5 into 10 to the power 28 per meter cube. 8.5 into 10 to the power 28 is number of copper atoms present per meter cube. M raised to power -3 means per meter cube. This amount of copper atoms is present. Since one copper atom is contributing 1 electron, So number of electrons in per meter cube of copper is also same, which is 8.5 into 10 raised power 28 per meter cube. Okay, so we have found the number density of electrons, that is 8.5 into 10 raised power 8 per meter cube. Now everything is known to us. Now put in the formula Vd. So this term is I upon, this is N, this is E, and this is A. Everything is known to us now. So now put the values. I is 1.5 ampere upon N is 8.5 into 10 raised power 28 into 1.6 into 10 raised power minus 19 into area was given 1.0 into 10 raised power minus 7. After solving, we will get drift velocity 1.1 into 10 raised power minus 3 meter per second. Also, we can write 1.1 millimeter per second. So now drift velocity is of the order of 1 millimeter, or we can say of the order of 10 raised power minus 3. Okay, I discussed about what is order. Order is 10 raised power how much? 10 raised power how much? So 10 raised power minus 3, that is the order of drift velocity for electrons in a conductor. That is, we can also say the drift velocity of electrons in a conductor is of order of millimeter. Okay, so we have found the drift velocity. So now note this value. We are going to use this in our upcoming part of this same example. So example 3.1 part B. Compare the drift speed obtained above with, so we have to compare this drift speed that we have calculated with thermal speeds of the copper atoms at ordinary temperature. This is the first part of B. Then after, we have to compare speed of propagation of electric field along the conductor which causes the drift motion. Okay, so we have to compare the drift speed with two things. One is thermal speeds of copper atom and second is speed of propagation of electric field. We have to compare the drift speed with these two things. Okay, so coming to first part. So first part, at a temperature T, the thermal speed of a copper atom of mass m is obtained from this thing. Okay, so this thing you have studied in kinetic theory of gases in 11th class. Okay, so in 11th class kinetic theory of gases, it is mentioned that average kinetic energy of an atom is equal to 3/2 kBT. Okay, average kinetic energy, this is given, average kinetic energy of an atom is always equal to 3/2 kBT. Okay, so this thing is shown, and this does typically of the order of root kBT upon m, where kb is Boltzmann constant. Okay, so what is this order? Okay, after solving this, you will get half m v square, average value of this equal to 3/2 kBT. Okay, after solving for this 2 and 2 will get cancel out, and v will be, you will get 3√3 kBT by m. But they are saying of order of. So in order, we are not concerned with the digit. Like in order of drift velocity, it was 1.1 into 10 raised power minus 3. So we can say it is of order of 10 raised power minus 3. We are not concerned with 1.1. Okay, so here also it is of the order of root kBT by m. We are not concerned with 3. Okay, actual velocity is equal to root 3 kBT by m, but it is of order of root kBT by m. Okay, where kb is the Boltzmann constant. So what is the value of Boltzmann constant? 1.38 into 10 raised power minus 3 meter square kg per second square Kelvin. Okay, this is the Boltzmann constant. So after putting this value and thermal speed at ordinary temperature, we have to find for copper at 300 Kelvin. So we have to compare the drift velocity with the thermal speed of copper atom at ordinary temperatures. Ordinary means room temperature. Room temperature is 25 to 27 degrees Celsius. Okay, we are taking 27 degrees Celsius, which is 300 Kelvin. So after putting T here, Boltzmann constant we also know, and molar mass of copper is given. And after putting this, we will get around 2 into 10 power 2 meter per second. That is the thermal speed of the copper atom. Okay, and this thermal speed is of the order of 10 raised to power 2 meter per square. Okay, what is the order of thermal speed? 10 raised to power 2 meter per second. This figure indicates the random vibrational speeds of copper atoms in a conductor. Now this is not speeds that atoms are moving here and there, because in metals atoms are fixed due to metallic bonds. Okay, so due to metallic bonds atoms are fixed, they can only vibrate, they are not free to move, only electrons are free to move. So here we can see that thermal speed is vibrational speeds of copper atom, not a simple speed, not a drift speed. Okay, it is only vibrational speed. So vibrational speed is of the order of 10 raised to power 2 meter per second. Note that the drift speed of the electrons is much smaller. Now we are comparing it with drift velocity. What was the drift velocity order? Order of drift velocity was 10 raised to power minus 3 meter per second. That is 1 millimeter per second. And order of this thermal speed is 10 raised to power 2 meter per second. Okay, so drift speed is much smaller than this thermal speed of copper atoms. About 10 raised to power minus 5 times the typical thermal speed of ordinary temperature. So it is 10 raised to power minus 5 times the typical thermal speed at ordinary. Means if we multiply thermal speed with 10 raised to power minus 5, it will become the order of 10 raised to power minus 3 meter per second. Means this drift velocity is 10 raised to power minus 5 times this drift velocity, thermal speed at ordinary temperature. Got it? So this is the comparison. Now second part, an electric field traveling along the conductor has a speed of electromagnetic wave. Okay, electric field is traveling with the speed of electromagnetic wave, that is 3 into 10 raised to power 8 meter per second. That is speed of light. Okay, you will learn about this in chapter 8, which is electromagnetic waves. Okay, that chapter is completely devoted to electromagnetic waves. So in that chapter you will going to learn that electric field travels with the speed of light. Okay, that is 3 into 10 raised to power 8 meter per second. Okay, so the order of electric field speed of the electric field is of the order of 10 raised to power 8 meter per second. Now we are going to compare it with drift speed. The drift speed is in comparison extremely smaller by a factor of 10 raised to power minus 11. I have explained in previous first part at how to do comparison. Okay, so it is of order of 10 raised to power 8. Drift velocity is of order of 10 raised to power minus 3. Okay, so it is 10 raised to power minus 11 times. Drift velocity of electron is 10 raised to power minus 11 times the speed of electric field. Okay, so you can compare this now. Now next example 3.2 A part. What is A part? In example 3.1, the electron drift is estimated to be only few millimeters per second for currents in the range of a few amperes. How then is current established almost the instant a circuit is closed? Okay, drift speed is only a few millimeters per second, like 1.1 millimeter per second we have calculated. Okay, so this small speed, that electron is covering only 1.1 millimeter per second. Okay, but if we are taking the conductor of 1 meter, then electron will take so much time to cover this 1 meter. Okay, so then how current establish almost the instant a current is closed, circuit is closed? When circuit is closed, we will get the reading of current. Then how current is established that fast if drift velocity is so small? Okay, so you have to think about it that electrons are present everywhere in the conductor. Okay, and speed of electric field is speed of light. Okay, so when we close the circuit, electric potential difference created and electric field is produced. So due to the speed of light, it will influence the electrons at that instant only without taking any time, instantaneously. So electric field is established through the circuit, throughout the circuit, almost instantly, because it is having speed of light. So it will establish throughout the circuit instantly, at that instant only, without taking any time, causing at every point a local electronic drift. Okay, due to which electrons present in the conductor everywhere feels the force. Okay, not only at that end, means if there is a conductor like this, if there are two electrons here and two electrons at that end, we are creating potential difference, and this is the direction of electric field. Okay, so electric field will establish instantly without taking any time. Okay, now electron will take time. The electron here at that end, this electron is at that end at negative potential. It will drift with the speed of 1 millimeter per second, 1.1 millimeter per second. So to cover that whole distance, of the conductor, it will take so much time. So how current is establishing so fast? If we are connecting an ammeter in the circuit, so current will start showing reading as fast as long as we are connecting this circuit and closing this circuit. Okay, so the concept behind is electrons are present everywhere. When we close the circuit, electron in that end also feel the force, and electron at that end also feel the force in the same direction. Okay, so local drifts in this region, local drifts happen. Okay, due to which all the electrons will experience force at the same time. Okay, so current will get established. Okay, like this. This is the mechanism. So current will electron will start flowing, but it is not due to a single electron at that end. Current is due to all the electrons present in the conductor. So establishment of a current does not have to wait for electrons from one end of a conductor traveling to the other. So establishment of current does not have to wait for electrons, that electron is coming from one end to another end. It is due to the all electrons present in that conductor, not due to the electron present at another end. Okay, however, it does take a little while for the current to reach its steady value. Okay, as we close the circuit, at that instant current is established, but it is not the steady value of the current. It will take very few or little time, very few time it will take to get steady value. Why? Because as we close the circuit, just before closing the circuit, the velocities of the electron are random. Okay, when we close the circuit, just after closing, it will have random velocity or small drift velocity. Okay, as we keep the circuit closed, drift velocity increases. Okay, so it will increases and it will go up to a certain limit before collision. Okay, so before getting to a steady value, it will increase. So current will establish but become steady after a little while. Okay, it will not get steady at that moment, but it will take very much few time. Okay, to get steady value. But at the instant when we close the circuit, current is established but not a steady value. It will increase to a certain limit. Okay, some value from 0 to 5 ampere, it will increase from 0, 1, 2, 3, 4, 5, but in a very short time. Okay, it will not go from 0 to 5 at that instant only. Okay, okay, example 3.2b part. The electron drift arises due to force experienced by the electron in the electric field inside the conductor, but force should cause acceleration. Why then do electron acquire a steady average drift velocity? Okay, so we have discussed that electrons experience force due to electric field. Also, force causes acceleration. Then why we are not considering acceleration when we are uh, saying that electrons have drift velocity, which is constant, which is equal to given by v equal to minus e capital E up tau upon m, which is constant for electrons for a given material. Okay, so why we are taking that drift velocity steady while there is acceleration? So the answer is within the derivation. When we derive this relation, we have seen that capital Vi is the drift velocity of one electron after some time ti. When we have done the derivation in our previous lecture, that capital Vi is the drift velocity after some time ti of one electron, and we are taking the average of that drift velocities. We are not taking that one velocity because electrons have to travel uneven distances between two collisions. The distance or time between two collisions is not the same for every electron or every collision. It is different. So when electron goes from one collision and another collision happens between this, the velocity before second collision is capital Vi, and it is different for every electron. So we have taken the average of that speed, and due to acceleration, we have taken the average of all the velocities, different velocities. That is the reason we are taking steady average drift speed and not taking acceleration. Okay, for each free electron does accelerate, increasing its drift speed until it collides with a positive ion of a metal. Okay, so its drift velocity increasing until it collides with another positive ion. It loses its drift velocity after collision but starts to accelerate and increases its drift speed again, only to suffer a collision again, and so on. Okay, so it will collide at one metal ion, then it will again acquire some drift speed, and its drift speed increases afterwards again collision happened. It loses its drift velocity. Okay, after losing its drift velocity, it will again accelerate and again attain some drift velocity and collide, and this process will go on so far. Okay, so these drift velocities are different for every case. So on an average, we are taking average of all the drift velocities. So this steady value is average, not a specific value. Specific value may vary according to the acceleration or the path covered, but average value is steady. On the average, therefore, electrons acquire only a drift speed. Okay. So part C, if the electron drift speed is so small and the electron charge is also very small, how can we still obtain large amount of currents in a conductor? Okay, we know that drift speed is 1 millimeter per second of that order, and electron charge is also very small, 1.6 into 10 to the power minus 19. Okay, this is very small value, and this is charge on electron. Then how can we still obtain large amount of current in the conductor in amperes, not in milliamperes, not in microamperes? We can acquire the current as 5 ampere, 10 ampere. Okay, so how? So solution for part C, simple, because electron number density is enormous. So there is large amount of electrons present in the conductor, that is of the order of 10 raised to power 29 per meter cube. That large amount of electrons are present in a conductor. Okay, so if we multiply, we know that current is due to the charge. Okay, so what is the charge present in the conductor? So we can calculate it with the number density. What is the number density? 10 is per 29 into charge on one electron, which is 1.6 into 10 is power minus 19. So if we will solve it, it will comes out to be 1.6 into 10 is power 10 coulomb per meter cube, because that is number density per meter cube. So that amount of charge is present per meter cube of conductor. Okay, we know that 1 coulomb is very large unit. Okay, in electrostatic, we used microcoulombs, millicoulombs, and picocoulombs. We didn't use 1 coulomb, rarely used 1 coulomb. Okay, so 10 is power of 10 order. This order of coulomb is very large charge. So this amount of charge is present per meter cube of the conductor due to the large number density of electrons present in a conductor. Even if its drift speed is small and charge on electron is small, but the number density is very large, due to which charge present in the conductor per meter cube is very large, due to which we obtain large amount of currents in a conductor. Okay. Example 3.2d. When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? So does it mean that all the free electrons of the metal are moving in same direction? If there is an electric field or there is a potential difference created, so does it mean that all the free electrons of the metal are moving in same direction? Okay, so you can take the idea from that thing, that before the application of electric field, if there is no electric field, absence of electric field, the motion of electrons is random due to thermal speeds. Okay, they possess thermal speed due to temperature, so their motion is completely random. Okay, so when we apply the electric field or potential difference, so electron will go from lower potential to higher potential, but because there is thermal speeds only also present. Okay, so the drift speed will not cancel exactly the thermal speeds. It will only provide electron specific direction to move. Okay, but thermal speeds are still there. That drift speed only overcome the effect of thermal speeds, but not completely cancelling it. That's why all the electrons are not in the same direction of the increasing potential. Okay, so also we have seen in the one diagram in our previous lecture that there is a blue line path which electron is following in the absence of electric field, and there is dotted path which electron is following in the presence of electric field. The only change in two paths is that dotted path in the presence of electric field is just drifted in the direction opposite to the electric field, but that random path is not changed, only drifted in the direction opposite to the electric field. So electrons possessing high thermal speeds will only get drifted by its actual path, but not exactly take same direction from lower potential to higher potential. Okay, by no means, not at all. The drift velocity is superposed over the large random velocities of the electrons. So drift velocity is only superposed, only overcome the large velocities of the electron, but it will not completely eliminates the thermal speeds, due to which all the electrons are not in the same direction, but most of the electrons will get the direction from lower potential to higher potential. Okay, are the paths of electron straight line between the successive collision? Okay, so are the paths of electron between two successive collisions a straight line with the positive ions of the metal in two cases, in the absence of electric field or in the presence of electric field. Okay, in the absence of electric field, electrons possess thermal speeds, so their path is straight line. But is it straight line in presence of electric field? Okay, solution is, in the absence of electric field, paths are straight line. In the presence of electric field, paths are in general curved. Why curved? Because I have told you in previous lecture that this is, here first collision happened, here second collision happened. Okay, so just after second collision, its random velocity is in this direction, small vi. Its random velocity is in this direction, but we have applied the electric field in this direction. Okay, after collision at point 2, its random velocity after collision, its random velocity small vi is in this direction, and we have applied the electric field horizontally in the forward direction. So just after collision, it will experience, sometime after collision, it will start experiencing the force in the direction opposite to this electric field. So this electron will now go like this. It will reverse its path and tries to align in the direction opposite to the electric field. So this path is curved now. Random velocity is in the direction of electric field, but after some time of collision, the force due to this electric field start deviating the path of electron, and it will perform a curved path and tries to move in the direction opposite to the electric field. Okay, so in the presence of electric field, path is generally curved, but in the absence of electric field, path is straight line, because that type of motion is due to only thermal conditions, not due to any external force. So our next topic is mobility, 3.5.1. So conductivity arises from mobile charge carriers which vary depending on the material. Okay, so what is conductivity? Is the opposite of, is the reciprocal of resistivity. Ability of a conductor to allow the flow of charges from them. Okay, so this is conductivity that arises from mobile charge carriers that are free to move, which vary depending on the material. So depending upon the material, conductivity varies. Okay, for silver it is very much large amount, and for iron it is somewhat small amount than silver. Okay, for silver conductivity is large, silver and copper. In metals, electrons serve as mobile charges. Okay, in metals, electrons are mobile charges that are free to move. Ionized gas. What is ionized gases? Okay, you may have done or studied about the cathode tube experiment in the chemistry chapter 2 11th. Okay, in cathode tube experiment, what is done? Potential difference is created, high potential difference is created, and gas is ionized, which means it is broken down into ions and electrons. The atom of the gases loses electrons and become ions, and gas atoms is divided into electrons and ions. This is called ionized gas, breakdown of gas. Have both electrons and positive charge ions. Okay, ionized gas have both positive charge ions and electrons. Also electrolyte solutions contain both positive and negative ions. Okay, what is mobility now? Is defined as the magnitude of drift velocity per unit electric field. Okay, expressed as, so mobility is represented by mu sign, and it is defined as the magnitude of drift velocity per unit electric field. Okay, so how much drift velocity is there for unit electric field means, what is the drift velocity of electron if we are applying unit electric field across the ends of the conductor. Okay, so that is mobility of that electron, and it is mathematically represented as this, magnitude of Vd upon electric field. Okay, so how much drift velocity of electron or any other charge carrier is there if 1 unit, means 1 Newton per coulomb or 1 volt per meter unit electric field is applied. Okay, so that is the mobility of that charge carrier. The SI unit for mobility is meter square per voltmeter square, as mobility is given by Vd upon E. Drift velocity, its units are meter per second. Unit of electric field is volt per meter. So meter square per volt second. This is the SI unit. Okay, which is 10 raised power 4 times the mobility in practical units. These are the practical units, means practically in practical example applications, this unit is frequently used, centimeter square per volt second. Okay, so this is the practical unit. So this is SI unit, which is 10 raised power 4 times the mobility in practical units. Mobility is always a positive quantity because we are taking magnitude of drift velocity and also magnitude of electric field. So it is a positive quantity also. Based on the relationship, now we know Vd is equal to magnitude of Vd is equal to E tau E capital E upon M. Okay, so we know Vd is minus E capital E tau by M, but magnitude is E capital E tau by M. We are eliminating negative sign. So mobility can be expressed as, put this Vd value in the expression of mobility. So Vd, put this there, E tau capital E upon M. So you will get this E tau upon M. So this is the, mark it as 3.25 equation. So this is the expression for mobility, where tau represents the average collision time for electrons. Okay, relaxation time, average time between two collisions. Now another topic, limitations of Ohm's law. So there are some limitations of Ohm's law also. We are going to discuss it case by case. So what is the objective? To understand the limitations of the Ohm's law. So Ohm's law, while valid for many materials, it is valid for many materials, especially metals or conductors, has notable exception where the proportionality between voltage and current doesn't hold. Okay, there are some conditions, there are some materials for which proportionality between voltage and current doesn't hold. Okay, so this proportionality can disturbed. The deviations broadly are one or more of the following types. So we have divided these exceptions into three cases. Case 1, V ceases to be proportional to I. When V ceases to proportional to I due to some conditions. Okay, for a material it is proportional, but after some time, if we are changing the conditions or we are changing anything between the material, V ceases, V stops to be proportional to I. So their proportionality will be disturbed. Case 2, diode-like voltage response pattern. So what is diode? That is some semiconductor material. Okay, so these type of material, diode, semiconductor, we are going to discuss in 12th class in the last chapter, semiconductor materials. Okay, and third case is non-unique VI characteristics curve. So for materials for which VI characteristic curve is non-unique, means for every unique value of voltage there is not a unique value of current, or vice versa. For every unique value of current there is not unique value of voltage. So non-unique VI characteristic curves. So first case we will discuss it with case by case. First case, when V ceases to be proportional to I. So this is the graph. So till here V is proportional to I, nearly proportional to I. After that it is start deviating from the proportionality. So this dotted line is the Ohm's law, perfect Ohm's law, where V is proportional to I. So this blue line is till that point it is proportional. After that its proportionality is ceasing. Okay, V ceases to be stops, means V stops to be proportional to I. Okay, proportionality is disturbing here. Why? Due to some conditions it can happen. Okay, if we are increasing the temperature, okay, if we are increasing the temperature of components, resistors and connecting wires, due to which this proportionality can disturb according to Ohm's law, because we have to fix the physical conditions like temperature. So what happens if we increase the temperature? Resistance get increased. How? We will discuss in detail in this chapter only, in the upcoming slides, in the upcoming lectures. Okay, so if we are increasing the temperature, resistance will also get increased, due to which if constant is increasing, V is proportional to I and V is equal to IR. This R should be constant, na? If this constant is increasing with temperature, then this proportionality will also get disturbed, na? Okay, so due to the change in physical condition, this proportionality ceases to be proportional. So the dashed line represents the linear Ohm's law. The solid line is the voltage V versus current I for a good conductor. Okay, so solid line is for good conductor. It is good conductor because it is proportional up to some limit. But after we are changing some condition, it is not no longer proportional to I. V ceases to be proportional to I in figure 3.5. Okay, second case. Diode-like voltage responses. Okay, in diode, what is there? We apply the potential difference across the end of the diode. Then we reverse the terminals. Means if initially this is diode material, if we are applying potential in this way, that this end is at positive potential, this is at negative. Afterwards, in second case, we will reverse the potential difference. We will change the sign of the potential difference across it. Now here, this end is at negative potential, this is at positive potential. This is called forward voltage, this is called reverse voltage. Okay, we are changing the sign of the potential difference or voltage across the diode material that is made up of semiconducting material. Okay, what are semiconductors? There are classification of materials, that is conductors and insulator. The materials that are between conductors and semiconductor in the terms of their conductivity and resistivity are called semiconductors. Okay, so they conduct, but their conductivity is less than conductors. Okay, but their conductivity is greater than insulators. Okay, so for diode, this is type of VI characteristic. If we are applying V in this direction, means positive and negative in first case, forward voltage. So this is the graph between VI. If we are reversing the sign of the voltage in the opposite direction, means positive potential terminal is now converted to negative and negative terminal is converted to positive. This is reverse voltage. So reverse voltage in negative direction. So current now varies as this. So both curves are not same. Okay, so their VI characteristic change if we are reversing the sign of the voltage across the diode. Characteristic curve of a diode. Note that different scales for negative and positive values of voltage and current. Okay, so also scales are different. Here current is taken as milliampere, here current is taken as microampere. Okay, and voltage, here voltage is taken as 0.2 volt, here 2 volt. Okay, the relation between V and I depends on the sign of V. Okay, the relation, that curve is dependent on the sign of V. Okay, if we are taking that forward voltage, positive voltage, okay, like I have mentioned that set this terminal as positive, set this end of diode is as negative. This is forward voltage, we can say. Okay, for forward voltage, current varies as this curve, as shown in the figure. Okay, it is not linear also. Okay, if we reverse the sign of this potential difference or voltage, if we are making this terminal negative and positive, so we are changing the sign of the V, voltage, reverse voltage in this direction. Now current will vary as this, like this. So both the curves are different. So the relation between V and I depends on the sign of V. In other words, I is the current for a certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current for the same magnitude as I is in opposite direction. Okay, if we fix the value of V, suppose 0.2 volt, and corresponding to that, this is the value of current. Okay, now if we take 0.2 voltage here, but sign is different, which is minus 0.2. Now corresponding to that, this is the value of current. But in both cases, for same voltage but different sign, current value of current will be different, not same. Okay, so that is expressed in this line. In other words, I is the current for certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of same magnitude as I in the opposite direction. So it will not produce the same current. Okay, because VI characteristic in both the cases is different. So these are diode-like voltage response pattern. Okay, you have to remember just this thing for now. Okay, we will discuss this graph in that chapter in detail. Okay, case 3, non-unique VI characteristic curve. Means there is not unique value of current for a unique value of V. There can be two values of current for unique value of V. There can be two values of V for unique value of I. Okay, so non-unique VI characteristics like this. For this, if we fix the current value like this, so this current value will correspond to two voltages. First one this, first one this. So it cannot happen according to Ohm's law. There is a unique value of current for unique value of potential difference. But here is non-unique VI characteristics. For one value of current, there are two potential differences. Okay, so this type of, here the region is non-linear. This is negative resistance region. Means if we are increasing the voltage, current is decreasing. Current should increase, but here current is decreasing, means negative resistance region. Okay, so variation of current versus voltage for gallium arsenide. Okay, gallium arsenide is also semiconducting material. For that material, this type of graph is formed. VI characteristic for gallium arsenide is like this. So gallium arsenide having non-unique VI characteristics. Okay, thermistor. Thermistor is also a semiconducting device. Okay, also thermistor is also having this type of graph, non-unique VI characteristics. The relation between V and I is not unique. There is more than one value of V for the same current. Okay, a material exhibiting such behavior is gallium arsenide. Materials and devices that don't obey Ohm's law are commonly used in electronic circuits. Case 2 and this case 3. These both cases we have discussed two graphs that are corresponding to semiconductor materials, and these type of materials are used in electronic circuits. Okay, you may have seen the electronic circuit and small components on electronic circuit. Okay, so there is some chip like structure also there having multiple terminals. Okay, black color, rectangular type, square type, or some cylindrical type components. Okay, capacitors are also there on circuits, and also these electronic circuits are made up of semiconducting materials that do not follow Ohm's law. Okay, now 3.7. Materials are classified as conductors, semiconductors and insulators based on their resistivities in ascending order of values. Okay, so resistivities, metals exhibit low. What is resistivity? Ability of conductor to resist the flow of charges from it, which is less for conductor because they allow the flow of charges from them. So metal exhibit resistivities ranging from 10⁻⁻8 ohm meter. Ohm meter is the unit of resistivity, to 10⁻⁻6 ohm meter. So very less amount of resistivity metals exhibit because they are good conductors. Insulators like ceramics, rubber and plastic possess resistivity that are 10⁻18 times greater than the metals or more. Okay, so insulators like this, ceramic, rubber and plastic possess 10⁻18 times greater than metal. Okay, so large amount of resistivity is there due to which they doesn't conduct. Semiconductors fall between these two categories. Okay, as I have already mentioned that semiconductor fall between these two categories. Their distinct characteristic is their resistivities decreasing with increasing temperature. Okay, their resistivity decrease with increasing temperature, that is their conductivity increases when we increase the temperature. For metal, if we increase the temperature, their resistance also increases. But for semiconductors, if we increase the temperature, their resistance decreases. The case is inverse as that of conductors. So their resistivities decreases when we increase the temperature. So what is the mechanism? We will discuss in that chapter only. Semiconductor resistivity can be reduced by introducing small amount of suitable impurities. Okay, so in circuits, we cannot increase the temperature because it is harmful for other components. Okay, to increase the conductivity of semiconductor materials, the other method is used by introducing small amount of suitable impurities, a property that makes them valuable for electronic devices. Okay, so in semiconductor materials, to improve their conductivity, small amount of suitable impurities are added so that it can be helpful for electronic devices. Okay. Okay, thank you. I hope you enjoyed the session.